let's take a look at the motion down the ramp. If we have a ramp and we're gonna let almost frictionless cart travel down it, and then a sphere, a wooden ball, roll down it like that. Which is gonna win this race? If I could roll them down at the same time, we could have only three options. The one option is tie. Second option is the cart comes first to the finish line and the sphere comes second. Or the third option is the sphere gets to the finish line first and the cart second. But I can't roll them at the same time, so I'm going to roll them one after another. At first, I'm going to roll the sphere. So I have here the motion sensor. It's connected to computer interface, and I have program. I can use this program to measure position of this sphere as a function of time. This ultrasonic sensor makes pulses. They travel to the object, get reflected like echo, and the system computes the exact location of this object at different times. I can then use that program to sketch the graph and analyze it. That's what I'm going to try to do. So. And now I can use the built-in options to get the equation for the graph that fits the best. It's quadratic function naturally, and this coefficient 0.2156 is equal to a half of the acceleration. The acceleration of the sphere will be equal to 2 times 0.2156, roughly 0.4 meters per second squared. Now, let's the cart move down. So we should imagine that this is icy, oily surface. The subject slides down without any friction acting on it. In reality, instead we use these almost frictionless wheels. The cart gonna move down, and I can measure the acceleration of this cart. All right, same procedure. And the coefficient now is 0.31. So the acceleration of the cart is about twice of that, 0.6 meters per second squared. Naturally, 0.6 is greater than 0.4. What does it mean? It means in terms of the motion, if they both start moving from rest, they will travel same distance in different time. An object with higher acceleration needs less time to travel this distance. So the cart will win this race. And what does it mean? Well, it means we kind of proved the fact that an object with less inertia wins the race like that. The sphere has more inertia because in addition to translational motion, it also rolls. So it makes rotational motion. So in addition to just mass as a measure of inertia, we also should take into account rotational inertia measured by the moment of inertia. So even though they have the same mass, this is harder to make move faster. And because of that, the sphere will lose the race between the cart and the sphere. So this experiment proves the fact that the object with less inertia will win the race. The object with more inertia will lose this race. And now what I want to do, I want to run down this ramp 3 different objects: a solid disk, a ring, and a solid sphere. They all have the same size, same radius or diameter, and they all have the same mass. That allows us to calculate the inertia, and we can see that in this situation because, well, the equations for inertia, rotational inertia, the sphere will have the least amount of inertia, and the ring will have the most of the inertia totally. So the sphere should win this race, and the ring should lose this race. In fact, you can use some algebra and the law of conservation of mechanical energy to carry out some calculation and calculate the speed of an object when it travels this distance. At the finish line, the speed will depend on the form factor, on this coefficient. Form factor is the coefficient in the moment of inertia of an object. For the ring, it's 1, for the cylinder, 1/2, for the sphere, 0.4. And because speed and time of the motion are related, then we can make a mathematical conclusion: more inertia, more time; less inertia, less time. And that means this is how this race should end. Well, let's take a look. Now I'm not going to measure acceleration. Now I'm just going to run these shapes down by 2 at a time. So first, let's run down the sphere and a solid disk. Which one's going to win? clearly the sphere wins this race. So we proved less inertia, more inertia, wins, loses. Now let's roll these two together. And now we can see the solid disk wins and the ring loses. So if we compare all four of these, then if we could run all four of these simultaneously, this card would win the race. Second place would be taken by the sphere, third place for the solid disk, and the ring would lose. And by the way, just a reminder, if they have the same shape and the same mass, why does the ring have more inertia, rotational inertia, moment of inertia, than the solid disk? Because of simple reasoning. The moment of inertia depends on the location of the mass. So it's mass radius squared. So when we increase the distance from the axis of rotation, we increase the inertia. And how can we make this from this without changing size or mass? Well, we have to use our imagination. We kind of push the mass away from a center until we move the total mass to the rim, to the edge. And by moving away the mass, we are increasing the inertia. And that's why, again, when they move from rest, same distance, this loses, this one wins. All right,